Oh, I don't want to get rid of that. Right then. Okay, we need to get rid of the music. One sec. Okay, hello and welcome to the November edition of the DigitalOcean Amsterdam meetup. We weren't going to do this, but thankfully the Brain Creators crew, they came in last minute, like literally on like Friday, and then they said yes to it on Monday, and today is Thursday. So I'm super grateful that these guys could come through, because we like beer and pizza, and hopefully machine learning will be really interesting. So here we are. I am David. I'm the guy who sends out all the emails. I'm the host for tonight. Before we start, I should probably say thanks to a few people who helped me make this possible. On the left, there's a very stern-looking Valerie. She helped me put out some chairs, threw out some beers, and did a very nice job with the sharks. Sharon, hopefully you saw her at the main door. She gave you a raffle ticket and a name badge. She also recommended the wines, because we didn't have very good wine last time, so she knows wine far better than I, so you can give her credit for that. And then Hugo has been running around crazily trying to get my live stream to work. There's a lot of cables, and sometimes it doesn't work as well as I'd like it to, but we like smash it and it works now, so that is good. Next slide. So yeah, the agenda for tonight, doors open, you managed to grab a drink. This is the introduction. We're going to blast through it because these guys have got so much content, we have to like squidge it into like 45 minutes, so I'll try to make this quick. So Gerbert, with that Dutch G, is doing machine learning tonight, which is great, and then we're going to have a little interlude, so you can grab another beer, go for a toilet break, and then Tom, he's doing deep learning. So that builds on the machine learning concept, and then straight after that we're going to have pizza, and then you can like chat and talk about stuff. So that's that. In the case of emergencies, I always do these, nobody else does these, but I'm like, right, we're going to do it. In the event of a fire, there's like fire exits behind you. You might have to climb across beer crates, but that's fine. Either that, or you go down the stairs down here, and the bridge is the fire escape point. You just chill out there with a beer, and we'll put the fire out, and then that is great. If you hurt yourself, find a member of Your Majesty or myself or Hugo or whatnot, and we will patch you up, give you some paracetamol, or like wrap you up. Hopefully we don't need any of this, but it's there. We have a first aid kit. We also have a code of conduct. This is more serious. A few people asked me why I put this in. Put simply, it just outlines the kind of protocols that we abide by, and everybody knows how to behave. If there is an incident, we can go, well, this is it, and it's just good practice, so it's good. DigitalOcean is dedicated to providing a harassment-free event experience for everybody, regardless of gender, gender identity, and expression, age, sexual orientation, disability, physical appearance, body size, race, ethnicity, religion, or that thereof, or technological choices. I'm not going to read the rest, but it is longer on the website. But that's the general gist: is just be nice to each other, and it'll be fine. If you feel like you can't adhere to this, then you can leave. But up to this point, only like one person has ever left. But I mean, I'm open to it. Nope. Okay. And then if there is an incident, you can always find me or any of Your Majesty crew, and we can talk about it. If you don't want to talk about it, you can tweet about it or send me an email. If you want to take it even further than that, you can talk to Samantha. She runs the DigitalOcean meetups globally, and all those details will be on like the final slide. So we need sponsors to make this happen. Your Majesty, who's the little crown, these guys, this is their office, and they let me do this. Give me time to put it together. And obviously DigitalOcean, they pay for all the beers and the pizzas and all the things that make it great. This is what DigitalOcean looks like, if you didn't know. They're the first cloud hosting provider to use solid-state drives everywhere. You can have a droplet in like 55 seconds, and this is what 55 seconds look like. And it gives you full root access, so you can do more or less whatever you fancy on there. So yeah, that's that. And then that means that you can spend less time doing like figuring out server things and getting really angry. I mean, you can still get angry, but it's just not at servers. And more time doing nerdy fun stuff. So that's good. And then yeah, the Your Majesty crew. We're a design technology firm that powers digital product. We do stuff like Netflix, Adidas, Samsung, Spotify, to name a few. Okay, yeah. Yeah, but what does that mean? So we put like last year we did some stuff for Adidas. We put like shoes on the side of cubes, and then we put them all over Europe. That was pretty exciting. We make horsey games in WebGL, which was quite fun. And we do a lot of stuff for Samsung Smart Things. We do their website, we do like their app, we do some in-store stuff. We put like videos on their smart TVs that tell you how to make them smarter, not in an AI way, just in a normal kind of way. And then we also go gallivanting around the world on trips, which is fun. Once a year, we went to Rome, and that was fun. I'm not going to go into it, but it was good. Yeah, and then the calendar. So it's Thursday.
I'm doing this presentation for the first time because it was short notice, and I sort of grabbed some stuff together, and I thought also a little bit more introductory stuff, a little bit more history. So I have no idea how I end up with the time, but I hope you enjoy it. So AI currently, it's hot. It's very hot. Everybody's talking about it. You see it in the news everywhere. And yeah, people are getting truly excited. But people also forget that the world is a big place. So in terms of comparing ourselves with the popularity of Britney Spears, we still have a way to go. So that I hope that sort of puts things in perspective. But on the other hand, you get these guys, the marketeers, who are projecting glorious gazillion dollar revenues over the next years. So that's nice, being an AI company. But yeah, it's basically a lot of hype, and people don't know really yet what it is and where you can apply it for. So there's a lot of research and development going on. So there's an explosion of these companies, some of them sort of specializing in particular domains, others are more infrastructure, and things are moving very fast. So there's a lot of myths about what AI is and what it can do. So the first myth is that people think they can just buy an AI and that'll solve the problem. It's not like that at all. Usually it's much more that you have to have the right data in order to even use the AI. So things are not as easy as just buying an AI as you buy a database or buy any other software. So other mistake is that people think AI is like human intelligence, which yeah, of course it's far from it. A lot of people are afraid that AI is going to take over the world, and we're sort of a bit far away from that. Although AI can solve a lot of complex problems, it's still primarily the human that controls the bigger flow of what is around. So you can have very effective specific AIs, but it's still a human that basically points it in the right direction in the first place. AI learns on its own. This is also a myth where most people believe that once you have enabled some AI project, then it will get better and better over time. It doesn't. You have to keep feeding it labeled data. So this doesn't happen naturally. Which also makes it different than other software projects, because usually when you deliver a piece of software, you're pretty much done. But AI has a little bit more of a maintenance long tail behind it. So what is it? AI can be many things. Even in my history talk, I won't highlight everything there is, because it's just too much and too detailed, which might get a little bit boring. So I'm just gonna talk about sort of how things got started. Well, back in the 18th century, people are already amazed about what's called automata. So this bird actually ingested food and shit it out on the back end. which was actually a little trick because it would actually collect the food in its belly, and the shit was prepared previously. But people, you know, they saw it and they believed it, and it would quack a little bit and open its mouth, and people are really impressed, and they're saying, what is the nature of intelligence? Where is life? You know, how do these things move? What does it all mean? So this was the first time where people were really presented with a machine that could tickle their mind in a certain way. So then, well, before all this, you had sort of these weave thingies where people started to do a little bit of computation, but basically only in the 20s, the first actual sort of computers in a very raw form started to emerge, because they weren't generic. Not until this guy, which is, as you all know, Alan Turing, which is the father basically of these little machines, computers. He wrote an excellent paper on computable numbers, and this basically set off the digital age as we know it. He also sort of invented the concept of a Turing machine is basically a computer. So you feed it information and it responds to it. The Turing test is also from him, which is sort of funny in my opinion, because the first time people were actually creating computers, immediately they were thinking about AI and how to distinguish a human from a computer. So the Turing test, for people who don't know, is you basically put a tester in one room, and then he has to guess if in the other room there's a computer or a human. And they can only talk to text or some other medium, but they can't physically see each other, so that's why he has to make a guess. Which initially seems like a very good idea to test intelligence, but is it? So things started moving quickly after that. This is a 5 megabyte hard drive, by the way, if you still know what a megabyte is, because I think we're all in the terabyte age these days. But this is insane, right? Yeah, still. So in this time, you know, you couldn't do a lot with computers in terms of computation, but you could make very complicated computation. So so most systems were based on rules, what we today would call regular programming, but in these days was also considered a form of artificial intelligence. These rules basically have a lot of heuristics in them, which means that a human basically found out from external information a set of rules that apply to the problem, and he basically shoves that in there so that the system starts to react the way we want. But the system it's not capable of discovering these things, or so they are applied from above. So that's why things are not generic enough to solve the problems that we're looking for. Now we move up again a little bit. So now we are, to Apollo mission, doing 100 operations per second. Keep that number in mind. I'm going to come back to that. Which is nice, cost them a lot. But then, in the 60s, these guys came along and they invented the perceptron. So the perceptron is the first idea of what a neuron is, which I will show you in a different picture. So this is a biological neuron. Left side you have your dendrites, the nucleus, and then the electricity basically goes down the line here through the synapses. So they basically created this idea of an artificial neuron where you basically have to say you have your inputs that you summon. There's an activation function which basically determines the point at which the neuron will fire. So it's as simple as that. And then when you put those together, you get what we call these days a neural network. But then things were not going so well because you could only solve simple problems with them. They didn't figure out yet how to make deep neural nets. So this guy basically wrote a report and said neural networks are shit. Do not use them. Even if you have multiple layers, it's not going to work. And everybody believed him. So things became quiet for a while. And we enter the 80s. And in the 80s, for the first time, backpropagation was successfully applied to multi-layer networks. So this was a big deal. So yeah, now for the first time, you begin to see that these things could work. There was one problem, although not enough computing power and not enough information. So still people
kind of things would work pretty well. So for faces, for example, you would think that contrast, the patches which detect contrast would work very well. But for texture and for clothing, maybe contrast wouldn't work. So you would have to spend a lot of time engineering those things. Then you would apply them on the image, you would get numbers out, and then you would have a vector, and then the vector you throw in a classifier, and then it's classified. So this is not a scientific number, but when I was working on those things, yeah, you would spend not so much on data. You would have a data set. You didn't need to have huge data sets yet, and you spend quite a lot of time on features and a lot of time choosing the classifier. These things work really well. So if you have an iPhone or a camera, all the face detection actually still work with an algorithm which is called AdaBoost and the hard features, the one I showed you. Nothing about neural nets. So neural net can also do it, but the older one works fantastic. Very efficient, no problem with that. Now, deep learning came, and Gerbert already mentioned it. It's a super cool domain. We already know what a neuron is. We have around 100 billion in our brain, give or take. So we have the most powerful machine on the planet. Everybody of us in the head. So these are all neurons. The little lines here are weights, and basically the idea is that we want to train the weights, so change the numbers over there. Deep learning is nothing more than adding a lot of layers in between. So on the left-hand side you have inputs, where your stuff comes in, being an image, being audio, being text, being anomaly, let's say a vector of sensor data. The output is what you want to come up with, a class, whether it's a pant or a pants or a cap, or whether it's a jazz song or it's a funk song. And in between you have all the hidden layers, which don't do with the transform information over time. And the more you have, the deeper it is. That's why it's called deep learning, right? Otherwise it would just be neural networks, which were something of the 60s. So let's say we have a lot of images which have been labeled. As Gerbert said, this is supervised learning, so you need to have time to label those. You put them in, and we do what is called forward pass. This is a very, 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 very rough approximation, so you cannot code this given the image and understand everything and go home and do it. But pretty much what happens is that there's a little patch which goes around the image and basically extract information from patches. It scans the whole image and it fills in the initial layer, and then information goes from left to right and it arrives at the end. And eventually you get a label. In this case you put in pants and it says cap, and of course that's the case, can be, because you initialize the weights randomly. So the network didn't know anything. It's completely stupid. Whatever you put in, you get a random label. In this case it's the wrong one. That's a forward pass. Now the task is, of course, we want to make sure that if you put that image, you get in pants, not cap, right? So we know what we want because it's supervised. We had a label. Someone spent the time to put labels. So we know what we're going to do. Now the task is we have to correct all those lines to make sure the next time you put that image, it's going to be more likely that you get out pants instead of cap. So you're going to correct all those weights, and that's called gradient descent and back propagation. So you propagate information back all the way to the beginning. You update the weights so the next time it gets more likely. And you do this millions of times. And you have to do it very fast, otherwise you have to wait 2 years, and that's why you have GPUs, what Gerbert was showing you. So next time you put in the image, you probably get pants. And you repeat this process a lot of time until you get a good enough result. So obviously you're not going to be able to go home and program this now. But the idea is the information goes from left to right, goes at the end, you have a label, so you can propagate the errors, and eventually by doing it over and over and over you get a good result. Now if you compare it to the past, where you had to think about the features very, very hard, those features are gone. You have images and you get an output. So now you spend most of the time gathering data and choosing the network and training it, but you don't spend time anymore designing features. So the features actually are designed by the network. It's a very, very, very big difference. So you could say we are less creative now, we just get a lot of data. It's not true, there is a lot of creativity in the network, but it's a tremendous shift. So actually deep learning is learning the features by itself. I'm going to show you something live. I need to grab a bottle as well, so at least I have 3 objects. Let's see. So if I click on here, we go here, we skip the tutorial because we are all experts of AI, and yeah, so what I'm going to do, basically I'm going to train a neural network with 3 classes. First one is going to be me, so I just have to press the button here and move around. Okay, that's me. So I'm going to be represented by the cat. So whenever I go in front of it, it's going to say it's a cat. Now we train it with only 1 class, so of course whatever you put in front of it, it's still going to say it's a cat because it only knows 1 class. So whatever you show, it's a cat. So now we train it with another one. Let's do myself. Well, I can also go away, and we just do. Well, I can be partially in the image. That's not really a problem. So I'm just gonna put this one. Plop. That's the bottle. So now when I go in, you see that's a cat, and when we put the bottle in front, it's now the dog. Incredible. And then now we take the whatever, this fantastic remote. I'm gonna train this one as well. Zerp. All right. So I'm a cat. This is the little rabbit. The little rabbit. Thank you very much. And then we got the bottle. And then of course, if you put them together, that starts to be really funny. Then you see that the probability of one and the other starts bouncing. You know, now it's more of a bottle. It's more of a that. So you get a fight, and then I can try to be in, and then I get myself in. So, well, it works really well. It's very efficient, and the reason why it works so well is because of something called transfer learning as well, and I'll get back to it in a second. So, but you know, it's actually, it can be really, really nice and simple. So, okay, it seems to work, cool. Now the big question is what's going on inside. So Gerberts was showing you the decision tree that you saw there. The nice thing of decision trees is that you can actually, if you get an answer, let's say you're a doctor and the algorithm of the decision tree tells you the patient is sick. So as a doctor, you want to know why do you think that the patient is sick. So, you know, the blood pressure was really high and the temperature was low and the leg was completely broken and was blood spitting out everywhere, so the patient was sick. And then the doctor can go and verify, yeah, indeed, you know, if blood splits out from everywhere, it's probably sick, so I agree. And otherwise, if he says, no, it seems to be, I don't know, the eyes are blinking very fast, and that's why he's sick, then you would say, I don't agree with that, so I'm going to go further. So that's a nice thing with decision trees. They tell you why a decision was taken. In a neural net, you don't get that luxury. So it's kind of a black box. But of course, as we have MRI for brain, we try to have an MRI for the artificial brain. And the idea is trying to find out what's going on in the neural net. And if you look at it from left to right, you have to get a little bit used to it. But bear with me. These things here look very much like edges and corners and, you know, this kind of very low-level things. You cannot really have a conversation about those things. You know, wow, how is the image looking very much like stripes or very much like blobs? It's not a very interesting conversation. Here it's more textures. Here is more parts of objects, and here is a bit more complicated objects. So you can start saying, you know, it does look like this kind of shape, which is more like a sailboat. So you can ask more high-level question. Is it looking like, you know, does he have 2 eyes and a nose? So what happens is that you go from low level to high level, more abstract. And that's the power of deep learning. The deeper it is, the more abstract representations you get. And, you know, it's like at the beginning you talk to a very young kid, and later on you talk to more of an adult person, and you can ask more complicated questions. It's a very powerful way to represent data. You can look at it in another way. This is the same network with different things, but this is, I think, it should be the first level. So the first level you see textures and blobs, and then you go higher up and you get dog's face, the part of a dog. These are kids, and you get a lot of animals and stuff. So it's more high level concepts. So again, you go from low to high. Okay, so far so good. You're gonna get the slides, by the way, so you can go through later at your own pace. So we got a bit deeper. This slide you already seen. So there are a lot of configurations, and I showed you one with images. So I'm going to show you something with memory. So for text, that's a standard network. Again, before we had an image, pants inside or cap, and you will get an output. You can also put in numbers. You know, the images are nothing more than numbers. Eventually, just every pixel has a number, which is 3 colors. You can put in numbers, and you get out just the output, which is another number. Now the difference between this and that, these are recurrent neural networks, is that here, if you put in twice the same input, you would always get the same result. There's no memory. So it's every time the network forgets. You put in something, it will forget what you put inside, and you put again the same thing. It's as if you would meet that thing for the first time. Here you have a memory, so the network is aware of what happened before. So it can remember things. And that's very important. You know, if you ever know someone which lost memory or has problems with the brain not having memory, it's really tough to survive. As humans, we need to have memory all the time. It's a fundamental element of intelligence. So what happens here is the network, because it has memory, can start for example, predicting when you put in a word, the next word. So you put is fun, so you would say machine learning is fun, you see here. So if you put machine, it would predict learning. And when you do learning, you would do is. So you can predict the sentence. So that's a way in which you can generate text. And you can only do this if you put memory in the network. Again, you're not going to be able to go home and program this, but it's just to give you a hint. Whenever you have network with memories, then you can start doing things with sequences of things, like text or audio. Of course, you don't have to necessarily put a word out. It can also be a vector, because again, it's just numbers. So what you can do then, you can take your sequence, convert it in numbers, and then you can reconvert it back from numbers. You do the symmetric process. So first you encode it, and then you decode it back. So you could do machine learning is fun, it becomes machine learning is fun. It's not a very intelligent process. The cool thing is that you can train the first part in English and train the second part in Spanish. So the vector representation here, it's a common thing, and you swap this one, you put Spanish, and then you put in English and you get a Spanish one. And that's how Google Translate works today. So they have this common representation, which are just numbers. They learn it on millions of words, and they swap this part here, and they can put in different languages. That's a very, very powerful thing. And it's all based on the fact you can put memory in the network. And that's an encoder and that's a decoder. And this one here is what we call embedding, so I'll come back to it later. Actually, I'll give you an example with an image. Even cooler, that's what Gerbert was showing earlier. You can put in an image. Again, this becomes numbers. Remember that if you put in an image or if you put in text or sounds, they're just numbers. So conceptually, it's the same thing. You put in an image, you get numbers, and then instead of converting it to an image again, you can then plug in the one which is decoding the vector to text. So then you put in an image, you get text out. That's what Gerbert showed when you get a caption. of the network are random. But you can take the weights from a pre-trained network, and then whenever you have new classes, instead of starting over there with the random weights, you start over here with the weights which are pre-initialized, and then you keep learning. So as if you would have a brain which was not fresh, it just had already knowledge of some concepts. They don't need to be the same thing, they need to be somewhat similar. So if you look at natural images, it helped to have a network which was trained on natural images. And if you would want to classify, I don't know, brain images, it would help maybe to have been trained on black and white images which are a similar thing. But it's very powerful, and it allows you to overfit less and train with fewer images. Right, so in theory, I would want to go through these scenarios with you to make sure that you find ways to get more and more data, because data is essential to train your models. But I'm not sure how much energy do you have to go through those. I can also stop here and we just have pizza. But
it's not here yet. So
okay, so we agree that I continue until pizza is here?
Yeah.
Right. I'll entertain you, move my hands, and just don't think about pizza. There's no pizza in the room. Okay, right. Quickly. As I said, data is fundamental to be able to train models. Models without data suck. They overfit, and you get the tiger sofa thing. Right. So we need data. So where do we find data? First point is data sets. It's true that they don't grow very fast, but you have to search very carefully. Whenever you start, if you would ever work in AI, first thing you have to think about when you start in a new problem, is there freaking data somewhere? You know, where can we find it? And there are all sorts of sites where you have data sets. This 197K is not the number of data points, and this is the number of data sets. And each of them might have millions of points. So it's a huge amount of stuff that you can search through. Great. So you definitely have to do your homework, check out, is there anything that I can already find? Prepare for me. These are data sets which already have labels, or maybe not, but they're all prepared, nicely packaged in a zip file. You can download it, floop, and you're ready to go. Very often you're not that lucky, but maybe you're working with someone which already has data. Remember the slides where we said 60% of the data of the future will be generated by companies? Awesome. So if you are working with one of those companies, or you are one of those companies, you might have data yourself. Good thing there is that we have more and more. Bad thing is that a lot of companies, a slide that Gerbert had where you would saw all the papers on the ground and it said, no problems, we have data. You know, they just collect data, but they don't label it, they don't do anything with it. So it's not nicely prepared. It's completely unstructured, it's a mess. So there you should think ahead, what do I want to do with the data? Which kind of problem do I want to solve? If I know which problem to solve, I can start collecting it in a smarter way. It's very, very, very important. Yeah, so that's basically what I said. Scraping, it's super awesome because of course there's a shitload of data on internet. So, and it's fully legal because Google is scraping you, and you know it's like monkeys which say please scratch my back, and I'll scratch you back sometimes. So it's fully legal, it's allowed, and it's websites actually want to be scraped by Google. Funny enough, they don't want to be scraped by someone else. I don't know why, but I think smaller companies are not as evil as Google. But anyway, scraping is it's really cool. I'll guide you through small project. Well, it's a big project, but very quickly what we did. So you scrape a lot of websites. You end up with a shitload of images that not necessarily labeled, or very much not so. And then you have to go through a very tedious process where you search for keywords, you do clustering. Remember the clouds of images that Gerbert was showing you? And a little bit of manual work, unfortunately. Then you end up labeling some initial set of images, and then you train the model. That's what we did earlier. Right. That's the one I showed you with the webcam, right? That works. So we do the forward pass, the back pass. Now you're an expert of gradient descent. You know exactly how it works. We're covered. Now, okay, so this is fundamental. It's late in the evening, but you need to understand this. It's so cool. Remember that we said left side is very boring things like edges and little shapes, and the more you go to the right, the more high-level things you can reason with. So if you want to have an interesting reasoning, you don't extract numbers here, but you extract them over there. The more to the right you extract them, the more interesting things you can ask. So this vector here, it's just a bunch of numbers. It sounds very boring, but you can use it for very interesting things, such as, that's probably the only formula between brackets I have in the whole deck. So let's say picture formula. So you know this as it's the operator distance. So imagine you want to compute the distance between these two bracelets compared to those. So as a human, you would say the bracelets on the left are further away from each other than the one on the right, right? These are more similar. But a neural network initially doesn't know this. It just sees pixels. So if things are gray, they're more similar or not. But if you extract the vector over here, it learns more interesting concepts. Another way of showing it is that on that vector space, things which look more similar to a human being end up closer to each other. So even if you would have a red cat, you wouldn't end up close to this one because it's red, but you would still be close to cats, right? While if you would extract the vector on the left, red things would end up next to each other because it just looks at colors and edges. While over here, it looks at more high-level things. Right, so we have this super tool which is called embeddings. So let's say you take bracelets, we had this 20 million things there, so we want to sort them quickly. Now we can sort them, we click on the first, and all of a sudden all those things are similar. So what you can do now is say, oh cool, those are we're going to call thin bracelets. Nice, we label them, new category, and you can do it, you can go through it pretty quickly. These are the leatherly thick bracelet. Then the only problem is having imagination with label names, but okay, we are creative, so that's fine. Shoes, the same thing, that's a bunch of shoes. Clearly I shouldn't be wearing those, right? And I could be wearing maybe something else. So you can sort them. And yeah, that's, you call those, I don't know, stripy sneakers or whatever, and then these are non-stripy sneakers, again, naming. And then now you got all the labels that you put in, so you can train again. Same thing we did. So it's tedious, but instead of having to sort those things manually, you can using this embedding to go much faster. So these are tools that you can use in AI. The result is what Gerbert already showed you. We had the thing, so you can click on that and it tells you these are, it's a type of accessory, bag, totes with 99% probability, and these are similar products. These are the colors, and these are bottom wear, pants, jeans, and white flare boot cut. Whatever. Yeah. Yeah. So it works really well. Right. You still with me? Pizza is not here, so we have an agreement. We continue. Sorry for that. By the way, I own the pizza company, so they would come only when I'm done. So. Okay, augmentation. And this is very simple. Gerbert showed you the slide where we had to recognize the logo on, remember, on the envelopes for fraud detection. So in some cases, you can actually be creative, and even if you don't have so many samples, you can create new ones with very simple rules. So in this case, you have envelopes. Envelopes are always flat. So an envelope will look, maybe it will rotate a little bit. The logo might be a bit bigger, a bit smaller. There might be some stains of water and other things, but it's not going to be 3D bent in whatever shape because it's always flat on the envelope. So you can predict those variations mathematically. You can write down those rules and and render different logos. So we start with from a bunch of logos, thanks Google, and then you take the logo and you pretty much create these variations. Right? You start with the version 0 of this augmentation generator. You put it in. You generate a variation for every single logo. You know the drill. You train the thing, what we did. You get out of performance, and then if it doesn't work well, you go back and say, shit, this logo didn't really work well. Why didn't it work in these samples? Oh, there were stains of coffee. Ah, shit, we didn't think about coffee on the envelopes. Okay, so let's also add coffee stains to it. And we also forgot about I don't know, oil stains and that thing and whatever, and lipstick kisses on the envelopes. So we're gonna do a lipstick kiss generator. The interesting thing, no kidding, you can take all those things from internet. So you can download kisses of, oh shit, pizza is there. You can download those things and paste them on, and yeah, then you're done. Right, I just want to show you this one. That's the generative adversarial network that Gerbert showed you. The two networks are fighting each other. That is a generator, that's a discriminator, and they have to basically, this guy here has to tell you whether it's a fake dress or a real one, and the one on the left is trying to generate dresses. It's really cool because you can use this to generate new samples. So whenever you cannot write down those rules yourself, it's more difficult to define what kind of variation a dress should have because you need to be a fashion designer. It's not like coffee stains and rotation of an envelope. You can use those networks to actually generate samples. So it starts from nothing, and this is evolution over time. And you see that they start becoming more t-shirty, more and more t-shirty. Granted, they look a bit like hard punk t-shirts. It's not really always the style of everybody. But it starts to learn all sorts of cool things, and the more time you actually let it learn, the better it becomes. And you can use those. You see some results here for t-shirts and for dresses. You can use this and feed them to your own database, and you can learn more. And the more images you have, the more you can expand your generative adversarial network, which will generate more samples, and you will go in a loop. Final one, and we're really done.
Don't hurry, don't hurry.
Is oh, there's not here yet.
It's
Oh,
the gluten-free pizzas.
right. Okay. So slowly, we have data simulation. Right. So, as you see from left to right, we're going from very simple things to very hard. So in some cases, either because it's very expensive or typically very expensive, like Gerbert showed you, the car crash. You don't want to drive a car around and just crash it and see what happens and learn from that. So you can use simulators. And this, the one on the left, is OpenAI Universe. So they did a really good job where you can pretty much take anything which runs on a screen, and you can put a network which will basically operate, will learn from what the pixels do on the screen and try to use the mouse and keyboard to act a bit like Super Mario game that you showed. He will learn from the pixels and try to basically press buttons randomly until he will learn what to do. That's really awesome because it works with anything which basically you can show on a computer. So you could teach a neural network to use PowerPoint if you really want. So you don't have to modify the software to have hooks to be connected to your neural network. If it has pixels, then this OpenAI universe can basically activate the keyboard, and you're done. It's a really nice framework. And then here you see on the left, it's the air simulation from Microsoft. It's for if you want to train drone algorithms to fly drones. And the one on the right is Deep Drive Universe. It's basically Grand Theft Auto 5. The interesting thing is that to create Grand Theft Auto 5, it took, I don't remember anymore if it was 20,000 man hours, but a shitload of time of software engineers and graphic designers to do. If you think about medical imaging and tasks that we can automate it's really nice. So short term, granted, it's not going to kill us. Long term, of course, nobody can predict the future in a lot of ways. As Gerbert would tell, then anyway, the universe would kill us, so it doesn't really matter. But of course, we cannot predict the future. So of course, it could be that eventually AI will kill us, and it's probably good to ask us questions about should we regulate it or not. But yeah, polarizing each other and fighting on Twitter is idiotic. So that's what we should definitely do. So can we have pizza now?
Yeah, maybe you want to do questions?
There's still no pizza. Man, okay, I'll.
It's coming.
Right, I don't know. I mean, I talk for a long time, so if you have any questions, shout. Otherwise, we can relax. That's it.
Nope, no one's got any questions. Okay, cool. Well, yeah, that was fascinating. Thank you for your in-depth thing about deep learning. I know a lot more than I ever thought I would about it, so that's great. It was also highly entertaining. Yes, so thanks again.
Very welcome.
If we could give me a round of applause, it'd be nice.
All right. Let's hope it comes in.
That's it. And then, yeah, hopefully pizza will turn up in a minute. It should have been here 25 minutes ago, but it's like, I'll give him a ring and be ring angry. When it does turn up, we already have gluten-free pizzas, so if there's like one person in here who does gluten-free, your pizzas are here already. We also cater for vegetarians. I will try to split up the vegetarian and non-vegetarian pizzas and label them accordingly. I'll try.
You need supervised.
Maybe, yeah, can we do some AI on that? That'd be great. And there's also a shed load of side dishes because they were doing a deal where you buy like a large pizza and you get like 2 side dishes. So I ordered 14 pizzas and I have 28 side dishes, which is probably why they're not here. Yes, so, and obviously most of those, except for like the obvious ones like buffalo wings and